We are diving straight into unsupervised visual chain-of-thought reasoning via preference optimization.
Let's just call it UV-UT.
Yeah, UV-CoT. This paper is a really big shift in how we're thinking about multimodal reasoning. It hits one of the biggest bottlenecks we have in MLMs today.
It all comes down to scalability. To get good visual chain of thought before this, you needed these massive, really expensive sets of human-labeled data.
Specifically, bounding box data for supervised fine-tuning.
Exactly. And UV-CoT just completely sidesteps that whole problem.
It does. The big idea here is moving image-level CoT into a totally unsupervised space.
Yeah.
They built this automated pipeline that generates its own preference data.
So it creates pairs of preferred and dispreferred bounding boxes.
And then it uses that data to train the target model, in this case, a Lavier 1.57b, with this specialized technique called Score-DPO.
Or SDPO. And the results, they really speak for themselves. This unsupervised system beats the previous state-of-the-art, including the supervised methods.
Right. And it generalizes so much better across data sets it's never seen before.
Especially on those really high-resolution, visually dense tasks. That's where it shines.
So in a nutshell, UV-CoT shows you can teach a model a really sophisticated, dynamic visual reasoning policy without any of the crippling annotation costs.
You just teach it how to rank its own choices. It's a powerful idea.
Okay, so let's unpack the motivation. For everyone listening, for MLLM researchers and engineers, text-based CoT it's a known quantity. It's a powerhouse. Why do we need to add this explicit image-level step?
Well, the limitation is really in the architecture's ability to handle high-fidelity spatial reasoning.
So even with a great text prompt?
Right. Even with a great TextCode2 prompt, most models are stuck with what the paper calls fixed granularity image processing. The model gets one look at the image, maybe processes some patches, and that's the entire context it has.
Meaning it can't, dynamically zoom in or shift its focus when it realizes a tiny detail is the key to the whole question.
Precisely. Think about a dense infographic or some complex schematic. Text alone can't tell the model, hey, look closer at this specific part. You need that localized visual cue. You need a bounding box.
So the first attempt at this, Visual CoT, it relied on supervised fine-tuning. People had to draw all those boxes.
Which sounds like a technical hurdle that just becomes an operational nightmare.
It was a huge barrier. First, the cost. Collecting and quality checking that much data is just prohibitively expensive and slow.
But there's a second, maybe more important problem, right, for generalization.
Exactly. SFT, or supervised fine-tuning, only learns from the correct examples, the positive examples.
And if you only train on what's right, you're not really learning how to handle ambiguity.
You're not. SFT just limits the model's ability to adapt to new, noisy, or just ambiguous scenarios where it has to figure out which regions are actually bad choices.
So UV-CoT is basically teaching the model to tell a good guess from a bad one.
Instead of just copying the right answer, it's a fundamental change in philosophy, trying to mimic how humans perceive things. We look at a region, we reason, we adjust.
And they pull it off using purely unsupervised data generated by the MLLMs themselves. The human annotator is completely out of the loop.
Which brings us to the core of the paper. This automated pipeline for generating preference data. It's all in their algorithm 1.
Right. They have two main models. The target model, which is the one they're training, that's LAVIA 1.57b.
And then an evaluator model, MLLM12b, which is there to, score the quality of the steps.
Using MLLM as the evaluator is a pretty smart choice, actually.
Why is that?
Well, it's a strong model, but it's not like calling a massive API like GPT-4. It's cheaper, more scalable. They were thinking about infrastructure from the start.
Okay, so the pipeline has two phases. Step 1 is region generation.
Right. You give the target model an image and a question, and it generates multiple potential bounding boxes. They use a template prompt for this, and importantly, stochastic decoding.
The stochastic decoding is key, isn't it? You need that diversity.
You have to have it. You need some good boxes, some okay boxes, maybe even some really bad ones, so you have those contrastive pairs to train on.
And then the model takes each of those bounded regions, little crops, and tries to answer the question using that view.
Which leads to step 2, quality assessment. This is where the evaluator model, MLLM, comes in and assigns a score to each of those attempts.
But here's where they do something really clever. It's not just about scoring the immediate answer. They call it cumulative evaluation.
They're looking ahead. The final score for a given step isn't just about the quality of the current response.
Right. It also incorporates the expected impact on the next reasoning step. They have this hyperparameter, gamma, that weights the future.
The formula is basically score equals current score plus gamma times the next score.
They're teaching the model to choose a bounding box that lends to long-term success, not just a quick win. A box that seems good now but traps you later is penalized.
And the ablation study on this was stark. I mean, setting gamma to 0 caused a massive performance drop.
An 8.8% average decrease. Can you break that down? What does that look like in a real task?
Okay, imagine the question is, what color is the car after it passes through the blue gate? With gamma at 0, the model might perfectly bound the blue gate, high current score. But if that box is too zoomed in and cuts off the car's initial color, the next step of reasoning is impossible. The whole chain fails.
So the gamma term forces the model to pick a slightly less perfect box of the gate if it means keeping the car in view for the next step.
Exactly. It's what makes it a true reasoning agent, not just a visual grounding tool.
So after all that scoring, they construct their pairs of preferred and dispreferred chains, and that becomes the training data.
And that data feeds into their new training mechanism. They couldn't just use standard DPO.
Why not? Direct preference optimization is pretty common.
Because standard DPO only cares about the ranking. This one is better than that one. But for visual reasoning, the degree of how much better it is matters a lot.
So this is where Score-DPO, or SDPO, comes into play.
Correct. UV-CoT puts the score difference directly into the loss function. It acts as a decision margin.
So if one bounding box is just slightly better, the model learns a weak preference. But if it's way, way better,
the model learns that this choice is fundamentally more important, and it needs a much stronger policy update.
So it's optimizing based on both the order and the magnitude of the preference. They ground this theoretically by connecting it to Gumbel distributed random variables.
That Gumbel distribution link is what allows the model to treat those larger score gaps as exponentially more significant. It moves it from a simple binary choice to a continuous weighted preference. It's a very elegant refinement.
But even with all that, they realized they needed one more piece to the puzzle, right? This iterative learning strategy.
Yeah, algorithm 2. This is to fight what's called distributional mismatch.
Which is when your model gets better, but the static data you're training it on was generated by the old, worse version of the model.
Exactly. It leads to drift. So they split the data into chunks. In each iteration, they use the current, slightly improved model to generate a totally new batch of preference data.
So the training data is always fresh, always relevant to the model's current abilities.
And again, the ablations proved this was essential. Generating all the data in one go and training once led to a 3.5% performance drop.
So it's really a triad of innovations. The look-ahead scoring with gamma, the magnitude-aware SDPO, and the iterative training. That's the whole engine.
Now let's talk results. The payoff. UV-CoT with 0 human labels hits an average score of 0.473.
Which is right up there with, and sometimes better than, the fully supervised Visual CoT 7B.
Which used 376,000 human-labeled examples. The efficiency gain is just staggering.
On specific tasks like text VQA and VSR, it was actually better by over 1%.
It just confirms that the policy you learned from ranking preferences is more robust than what you learned from just imitating human annotations.
But here's the finding that really made me pause. UVPT isn't just knowledge distillation.
No, because it actually outperforms its own teacher.
It outperforms the evaluator model, MLLM 12B, by 5.1% on average. How is that even possible?
It's because it wasn't learning to mimic MLLM's outputs. It was learning a better reasoning policy. MLLM just provided the scores, the definition of good and bad.
The SDPO process used those scores to optimize LFA's own policy for ranking choices.
And the insight there is that for an MLLM, ranking a few generated options is actually an easier and more tractable task than generating a perfect bounding box from scratch.
So it learned to be a better critic of its own work, which led to a better overall strategy.
The generalization results were also fantastic. It did great on unseen datasets like DUDE and Visual 7W.
But we have to talk about the V-star bench results.
Yes, the high-resolution benchmark.
Why is that the ultimate test for this?
The images are huge. Average resolution is something like 2200 by 1600 pixels. Dense documents, detailed charts, tiny text you need OCR for. This is where a fixed granularity model just completely falls apart.
And UV-CoT? It
crushed it. It beat the non-CoT baselines by over 50% on OCR tasks and beat the supervised Visual CoT by 5.5% on average.
That's the proof right there. When the visual field is dense, the ability to pick the right spot to focus on pays off massively.
They also looked at visual token efficiency. And even though CoT uses more tokens in theory, you process the full image and the crop, it was more efficient.
The quality of the region selection is just so high that the extra tokens are used optimally.
And for anyone thinking about deploying this, there was more good news.
The self-evaluation ablation.
Right. They tried using Elavia 1.57b as its own evaluator instead of the bigger MLLM model.
And the performance drop was tiny, only 0.2%.
Which means you can run this whole pipeline in-house. No need for expensive, larger teacher models or external APIs. That's a huge win.
Just to really drive the point home, they did one last experiment. They took the bounding boxes generated by UV-CoT and just fed them to a standard MLLM, MLLM.
And just giving it the location of where to look improved its performance by 7.4%.
So the regions it's generating are just fundamentally high quality.
So for you, the researcher or engineer listening, what's the big takeaway? UV-CoT is a scalable, data-efficient way to do image-level CT.
It dramatically boosts visual comprehension, especially for complex spatial reasoning.
And the key design insight is that combination of stability and foresight. The iterative loop prevents drift, and that gamma parameter ensures the model learns a policy that plans ahead.
But this brings us to a final provocative thought. It comes from their own limitations section.
Right. On the really complex document tasks like DocVQA, they ran one more test. They replaced UV-CoT's predicted bounding boxes with the ground truth ones.
The perfect human annotated boxes.
And the performance shot up. I mean, a huge jump. A score of 0.618 with ground truth versus 0.494 with UV-CoT's predictions.
So while this preference optimization policy is incredibly effective,
that gap tells us that the precise localization of the key region is still the critical bottleneck, especially for the most fine-grained tasks.
Which means the next frontier isn't just about refining the reasoning policy further, it's about integrating a truly world-class region proposal algorithm.
An advanced detector to feed the policy better initial guesses. The reasoning policy is ready. The detector now needs to catch up to it.